hello, 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 hello. I guess I'm talking there. That I'm hoping my jacket doesn't keep hitting the microphone, making it go. Sorry, you came too late. There you go.
Thank you.
Yes. And I suppose Issa thinks that she should also get these notes. Did I give you any? Oh, okay. Well, no, you don't get any. But here, Issa, you can have some. So hang on. No, I'm just kidding. Of course you get some too. There you are. All right. So, first thing we're going to talk about here, just because it's where the book chooses to do it, is actually not about light per se, but about how we measure the distances to stars, namely using parallax. So I always like to do this silly thing because you know what? If I look silly and y'all look silly, it's fine, as long as we're all looking silly here. So I want you to hold your thumb close to your face and blink back and forth, left, right, left, right. What do you notice that your thumb appears to be doing relative to stuff in the background? Shifting back and forth, right? And if you move your thumb further away and do the same thing, does your thumb appear to shift more or less than when it was close to your face? Less, right? So what's going on is parallax between your two eyes. In other words, you see your thumb in front of whatever is from the line of sight to the eye in question to your thumb, continued to the background. And when your thumb is closer to you, there's a greater angle between those two lines of sight than when your thumb is further away from you. That's the parallax between your two eyes. And it's the reason you have two eyes in the first place, mostly. In other words, it gives you depth perception. Your brain, without you having to be consciously aware of it, is comparing the two images from your two retinas and noticing the parallax of objects at different distances and using that to bring the world into the third dimension for you. You actually feel it three-dimensional. Things actually look like they're out there versus close to you and so forth, which is pretty remarkable. And so that's why we have two eyes. There are other creatures where their eyes are more on the side of their head, and so they don't get really depth perception from it. What they get is closer to a 360-degree field of view. So some creatures, that's more important to avoid getting eaten, for example, whereas with us, apparently, it was more important to have good depth perception. Now, don't know about you, but when I look at stars at night, or the moon, for example, well, I can't look at the moon and say, gosh, I can tell that it's closer than the stars are. I can't look at Mars and say, wow, I can tell Mars is closer than the stars are, because it turns out that those are so far away from us that there's no measurable parallax between your two eyes. And so, of course, we need to have a better way to do this, have something that's more viable. So by the way, the top there is this idea, as you have in your figures there, the top is figures showing this idea of parallax where somebody's holding up a pencil and you're comparing the view, the shift when the pencil's far away versus nearby, all that stuff we said, that the angle of shift is greater when something is closer to us. When it comes to stars, we need a longer baseline. We need a larger separation than is provided by our eyes, obviously. Well, it turns out that we are riding on a spaceship called Earth that makes a 2 AU swing around the sun every year. So if we can observe a star 6 months apart on opposite ends of our orbit, then maybe we could get a measurable parallax, a measure shift in the position of that star relative to the background stars. And of course, it's not just a maybe. We can if the star's close enough. We wouldn't be talking about this if this wasn't actually possible to pull off. And so the idea is here. Here is pink star A, blue star B. Star A is closer to us than star B is. By the way, that's pink, that's not yellow, so I will concede that. That's pink, right? We'll go with that. Little private joke there. Had a little debate before about whether something was pink or yellow, and so we had some differing opinions. But here I'm pretty sure we'll go with that's yellow, that's pink, right? Okay. I mean, if you're colorblind, it may not be to you. You're not, color blindness isn't a defect so much as it's just you see things differently because you don't have as many channels. You don't see anything wrong. Colors are created by our brains. They're not part of the external reality. At least the qualia are. Okay, I'm wandering a little off track here. Anyway, back to our story. So we've got Earth today, Earth 6 months later. And so we see a shifting line of sight to the two stars. And the line of sight, the angle between those two vantage points is larger for star A, right? If you measured this angle right here, than it is for star B, this angle right here. And we call half the angle of shift, not the whole angle, but half the angle of shift is what we call the parallax for the star. So it would be this angle right there. And I'm about to draw this on the board in a minute here. So it's just the definition that half the angle of shift is the star's parallax. So in the same way, astronomers use the changing perspective of Earth through the year to measure distances to stars. Star B is twice as far away as star A and appears to move half as much as star A over the course of the year. So if we very carefully measure stars, we can see them shifting relative to background stars depending on how close they are to us. There are stars far enough away. Most stars are far enough away. Too small to, the parallax is too small, at least from Earth-based telescopes. And I should point out, this is way, way, way exaggerated. In other words, you would never see a star shift that much relative to a bunch of background stars like this. So before I start getting a little more quantitative here, what questions do you have? Just wanted to establish the basic idea here first. Yes?
What, would you be able to figure out the distance away a star is if the parallax is too small?
So this is the only direct way we have of measuring stellar distances, right? So this is trigonometric, unassailable. It's a direct way to measure stellar distances. Now, as we'll see, once you've established distances for a bunch of stars using parallax, well, then you can do things like, okay, I know I've measured the distance to stars of spectral class A1, and I've measured their brightnesses, and that allows, by using parallax, and then I can use the distance and the brightness, how bright it looks from Earth, to determine its actual luminosity, how bright it actually is. And if we see other stars of spectral class A1 such that their spectral lines say that they are of the same luminosity class, main sequence versus subgiant versus giant and so forth, well, then we can use what's called, its terrible name, spectroscopic parallax, to determine distances of other stars where from the spectrum we can deduce what type of star it is, and from nearby stars of that type we figured out what their luminosity is. So for the more distant star you say, well, I know its luminosity and I can measure its brightness and use that to infer the distance. But that's an indirect distance determination, whereas parallax is a direct distance determination. So no, we are not stuck on only parallax to determine star distances, but you have to calibrate with parallax for nearby stars before you can extend to further away stars that are too far away to measure their parallax and infer their distances indirectly. Good question. What other questions do you have? Yes?
So is it only work if we know one of the star distances already?
No, because what we do need to know is the size of Earth's orbit around the sun. So in a minute I will show the diagram with the trigonometric relation that tells you how far away it is. But in other words, with a little trigonometry, if you know the distance between your eyes and you know the parallax angle, you can use trigonometry to say how far away something is. You could take two photographs, two cameras, or the same camera that you shifted, known distance apart, and by measuring the parallax angles, you could figure out how far things were from the camera lens, and your brain implicitly is doing that with your eyes as well. So here, what we need to know is the baseline. What we need, this in and itself would just tell you how far away the star is compared to the distance of Earth from the sun. But once we know the distance from Earth to the sun, we've got that calibration, and then we can say how far away the star actually is in meters or parsecs or whatever units we want to use for that. And then the other piece is just to point out that in practice, the star will only appear to move back and forth in a straight line if it is in the plane of the ecliptic, if it's in the plane of our orbit around the sun. In general, the star will be not in the plane of the ecliptic, and it will trace out what we call a parallax ellipse. So in other words, if a star was perpendicular, the line of sight to the star was perpendicular to the plane of our orbit around the sun, then as we move our very nearly circular orbit around the sun, the star will trace out a little circle on the sky as a result of that. And if it's at some other angle, it's not within the plane of our orbit, but it's also not perpendicular to it, then it traces out a flattened ellipse. The projection of our circular, nearly circular orbit would be an ellipse. So in general, what we observe is a parallax ellipse, and so we determine essentially the semi-major axis of that little ellipse in angle on the sky. Half of that is the star's parallax. That's the angle that we're actually measuring. Okay, so let's draw pictures to be quantitative here. And I'll just keep going back and forth to get the whole board visible here. So I've got a wider, what would I call it? Arena for operation or something, I don't know. Anyway, there we go. So let's draw a picture here on the board, and I'll just make the simple case of where the star, the direction of the star is in the plane of the board, and our orbit around the sun is in the plane of the board. So, and by the way, do you know how we know how big an AU is? The distance to the sun? Turns out these days it's radar. So in the first determination came from like the transit of Venus, for example, back in the 1700s. You could see a little bit of parallax. Different observers would see a shift in the position of Venus relative to the star, the solar disk. You could determine the distance to Venus that way, and Kepler's laws tell you the ratio of the size of our orbit to the size of Venus's orbit, and so people could infer the size of our orbit from that. The parallax would be based on how far apart the observing stations were on Earth. But now what we do is bounce radar signals off of Mercury and Venus in particular, and time how long it takes the signal to go from there to there and back. And then, because we know from Kepler's laws the ratio of the size of our orbit to their orbits, we can determine the size of the astronomical unit, and it's now known by that to a precision of 1 centimeter, believe it or not. We know the semi-major axis of our orbit around the sun to a precision of about 1 centimeter based on radar measurements, bouncing radar off of like Mercury and Venus, which is pretty cool. So anyway, oh wait, I have to apply the principle. Draw the first circle, the big one, and then put something in the middle, right? So here's Earth's orbit, and here, there's the sun in the middle there, right? Happily shining upon us. And so here is 1 AU, and of course, really, you know, the sun and the center of the sun orbits the center of mass, blah, 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 right? But again, very close, so to the center of the sun, so I'm ignoring things like that. And also, Earth's not the only planet, la, 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 la. So 1 AU, and also Earth's orbit is elliptical, not circular, blah, blah, blah. I'm just drawing it as a circle, you know, as an approximation here. So here is Earth, 6 months apart, and okay, let me, I guess I'll draw the lines. You know, I was going to draw the star and then try to draw lines to it. No, that's dangerous. I'll draw lines and then the star will just be where the lines intersect. By the way, not to scale any of these things, right? Stars are at a minimum hundreds of thousands of times further away from us than the sun is. So we're drawing those pictures with the star way closer than it should be, just in order to make the diagram, you can actually see what's happening. So do keep that in mind. One thing I emphasize, like in Astronomy 111, and I guess I'll emphasize with you too, right? You would be surprised how many people think that we put telescopes on mountaintops or in space in order to get them closer to the stars. Oh my God, please do not think that that's the reason why we do that. So as I always like to point out to the students, and I'll point it out to you too, so if Earth was represented by a 1-foot globe, the Hubble Space Telescope's orbit is about 1/3 of an inch to scale above that 1-foot globe. And the sun, the nearest star, is more than 2 miles away on that scale. And then other stars are hundreds of thousands of times further than that. Hundreds of thousands of miles away at a minimum. And so saying that you're putting the Hubble Space Telescope into space to get it close to the stars is like imagining that you've got something for even the sun 2 miles away, and you're saying, like, wait, it's 2 miles away up there, something, a balloon 2 miles away up there, and you want a better look at it. And so you stand 1/3 of an inch closer, and oh, that's much better. Oh, now I can read it, right? And then other things other stars on that scale are further away than the actual moon. Did you ever notice that? If you go outside and the moon's overhead, if you go like that, you can see all the craters. You don't even need a telescope, right? Nah, right? So no. I always tell them, I'm going to put a thing on there. Why do we put telescopes in orbit or on mountaintops? Be a multiple choice. One of the answers will be to get them close to the stars, and I say, I will cry if you put that answer, and every time there's at least one student who makes me cry. No! Okay, anyway. Now most of them don't. And a more common thing is they circle that and they say LOLDH, and they put something better than that, but still. Anyway, so there is a star. I'll make it a little 5-point. I'm sucking at this. Here, let's make it a cute little, fake 5-point star there, right? So there's our star. And we will say that its distance from us is D, right there. And here is P, the parallax angle. And notice, by, what do you call that? Like, opposite angles or opposite interior angles are equal. So both of those angles right there are P, the parallax, as is that one. There's 4 P's on there. Okay, so, and then this is going to represent way back here are much more distant stars. So way further away than I'm indicating here. Just kind of decorative here. Very distant stars. I mean, all stars are very distant, but I mean, these are very, very distant stars. So far away we can't see any parallax. Stellar parallax. P is the so-called parallax angle, or just the parallax. And, well, look at this. We've got us a right triangle right there. and the distance is one side and 1 AU is the other side with angle P there, right? So 1 AU is the side opposite angle P, and the distance to the star is the side adjacent to the angle P. So the distance in AU, astronomical units, the semi-major axis of Earth's orbit, distance in AU is given by the tangent of the parallax angle is equal to the star's, is equal to 1 AU over the star's distance, right? Just looking at that right triangle right there. The tangent of the parallax angle is 1 AU divided by the star's distance because, as we all know, SOHCAHTOA, right? Tangent is opposite over adjacent, right? All that business. That weird SOHCAHTOA stuff that I saw one year when a bunch of people were doing that. Anyway, so yeah, TOA says, right? And so, therefore, D is 1 AU over the tangent of P, but if we measure P in radians, what's true for small angles for the tangent of P if P is in radians? That's not what I'm looking for here, not 1. I'm looking for a small angle approximation here, which says that for theta small, sine theta and tan theta are both approximately equal to just what? Just theta by itself. Yeah, just theta by itself. So this is approximately just 1 AU divided by P, where P is in radians. Right, that's from that small angle approximation. That says that tan theta is approximately equal to sine theta is approximately equal to theta for theta being very small. Do you know in degrees about where that breaks down? I mean, of course, it's gradually breaking down, but do you have a sense of about how big an angle can we get before it starts to be not that great an approximation anymore as a rule of thumb? The answer is about 30 degrees or so is when it really starts to kind of fall apart. So you can actually get away with it for fairly large values. So if we express P in radians, then the distance is approximately 1 AU over the parallax. But parallaxes are so small that radians are a terrible unit to use to express them because the parallax will always be very tiny in radians. I'm assuming I can erase this. It's too late. It is more convenient to express P in arc seconds. That's what we usually use. In arc seconds, which we use hash to represent. And remember that 1 degree is what fraction of a circle? Yeah, how many degrees in a full all the way around? 360, right, is 1/360th of a full circle there, right? And 1 arc minute which we write with just a single hash like that, kind of looks like 1 foot in silly units, but here it means 1 arc minute is what fraction of a degree? 1/60th of a degree, 1/60th of a degree. And 1 arc second That one double hash, one double quote, if you will, is what fraction of a minute? It's just like time. No, what fraction of a minute? That's a degree. So what fraction of a minute is it?
1/60.
It is 1/60th of a minute. Just like a second of time is 1/60th of a minute of time. We make the same definition with angle here. One second of arc, 1 arc second is 1/60th of 1 minute, which is a 60th of a degree. So it's 1/3600th of a degree. So it's a very small angle. 1 arc second is 1/3600th of a degree, but we tend to, well, we measure parallax in arc seconds, we usually express that way, because there's no star, other than the sun, there's no star with a parallax of even 1 arc second. All parallaxes, all stellar parallaxes are less than an arc second. So radians would be terrible because, you know, a radian is like 57 something degrees. And so, yes.
Why don't they have another layer down? 1 arc microsecond or something?
Well, we do sometimes talk about milli-arc seconds and micro-arc seconds. Yeah, so that's there. Yeah, that is a thing as well, as a matter of fact. So the Hipparcos and satellite, and then following it, the Gaia satellite can measure parallaxes of milli-arc seconds. So, 1 radian, right, is equal to, let's convert that into arc seconds. Well, that's 1 radian times 360 degrees into pi radians, right, because in radian measured, full circles, 2 pi radians, times 3,600 arc seconds in 1 degree is 206,265 point something something arc seconds. 1 radian is 206,265 arc seconds. So that the distance in AU, given the parallax in arc seconds, is 206,265 over what we'll call P double prime, if you will. P in arc seconds, AU. P, that symbol right there, P double prime, so to speak, is the parallax in arc seconds. So measure the parallax in arc seconds, and the distance is 206,265 AU. So if the parallax were 1 arc second, how far away is the star in AU? 206,265 AU, right? So in other words, for a parallax of 1 arc second, you'd have to be 206,265 AU away. And notice there's a dual way that you can interpret this here. In other words, making a mini version of my diagram there. Here's the star. Right? There's the parallax angle. There's the parallax angle. Notice P is, because of the opposite interior angles business, P is both half the angle by which the star shifts back, appears to shift back and forth over the course of the year because of the fact that we're going around the sun. Half the angle the star appears to shift back and forth over the course of a year. Shift back and forth in a year. And it is the angle subtended by 1 AU at the distance to the star. In other words, right, since this is 1 AU, to subtend, for an angle, to say something subtends some angle, it means it just spans that angle. Like if I look at the moon and I imagine pointing at the quote-unquote top of the moon and at the bottom of the moon, the angle between those two directions is the angle subtended by the moon. Anybody happen to know about what angle the moon subtends on the sky? About half a degree. About half a degree is the angle subtended by the moon on the sky. It's about half a degree across on the sky. How many arc minutes? How many arc minutes in half a degree? How many in a whole degree? How many arc minutes in a whole degree?
160.
So 1 arc minute is a 60th of a degree. So how many arc minutes in a degree?
Or 500.
No, you're overdoing it. If an arc minute is a 60th of 1 degree, it follows that 1 degree is how many arc minutes?
60?
60, yeah. So there's 60 arc minutes in a degree. The moon subtends half a degree, so the moon subtends how many arc minutes?
30?
Correct, yes, 30. The moon subtends 30 arc minutes. The smallest angle that our eyes can perceive, can detect, is about 1 arc minute, about 1/30th of the size of the moon on the sky, which is why we can't see craters on the moon. The resolution of our eyes isn't quite good enough. There are birds of prey where the retinal cells are packed densely enough that we can determine that their angular resolution, we call it, of their vision, they can see craters on the moon just by looking at them. Unfortunately, they're not able to say, "Wow, craters on the moon." You know, they can't tell us this, but they can see craters on the moon. They probably don't say, "Wow, there's craters on the moon." They just don't think about it, but they can see craters on the moon. We, however, are not quite so fortunate. We don't have quite that resolution of our eyes. But notice, in other words, that if you were at the star, Earth's orbital size of 1 AU would subtend an angle equal to the parallax that we see the star shifting back and forth relative to more distant stars in the background. So keep that in mind. The parallax is both half the angle at which the star shifts back and forth on the sky as seen by us, and it's how big the radius of Earth's orbit looks at the distance to the star. Our orbit subtends, a radius subtends an angle of that same value, that parallax. And so a star that was seeing our orbit being 1 arc second in angular radius, such that we would see it shifting back and forth by 2 arc seconds over the course of the year, because remember the parallax is half the shift, would be, again, how many astronomical units away from us? If the parallax is 1 arc second, how far away is the star in astronomical units? 206,265 AU. So how many times further away from us is it than the sun? 206,265 times further away from the sun. For a star with a parallax of 1 arc second, it would be 206,265 times further away from the sun. The star with the largest parallax is Proxima Centauri, and that's about 0.77 arc seconds. So in other words, there is no star that even ever has a parallax of 1 arc second. They're all further away from that. Even the closest star other than the sun is further away from that. This is why it wasn't until 1838, I think it was, that the first parallax was finally successfully measured for a star called 61 Cygni. That was the first time that astronomers knew literally how far away stars were from us compared to the sun. So, let's make a more reasonable measure here, right? We don't want to say stars are so many hundreds of thousands of AU away. Why, let's define 206,265 AU to be 1 parsec. That's what we're going to do. Did you have a question?
So greater the parallax in arc seconds, closer the star.
That's right, yes.
And speaking of moon, is it that in every 30 minutes it moves half a degree in the sky?
So we have to be careful because the angle it subtends is 30 arc minutes, okay? But that's not directly related to how long it takes the moon to move a given distance on the sky. So in fact, when you run all the numbers, so the sky turns 360 degrees in 24 hours, right? And so that means that it turns, in 1 hour of time, it turns through 15 degrees. The Earth rotates 15 degrees in 1 hour of what we call sidereal time. And so that means, let's see, so the sun and the moon are both about the same size on the sky. That's why we can get such an almost perfect total eclipse. So they are both half a degree across on the sky, right? And the sky turns 15 degrees in an hour. So how far does the sky turn in degrees in 1 minute if it turns 15 degrees in 1 hour? So the sky turns 15 degrees in 1 hour. So how long does it take the sky to turn through 1 degree? If it takes 60 minutes to turn 15 degrees, how long does it take to turn 1 degree? Yeah, 4 minutes, right? So it takes the sky 4 minutes to turn through 1 degree. So how long does it take to turn through half a degree, which is the size of the sun and the moon on the sky? 2 minutes, right? So if the sun, if you're like near the equator where the sun's rising pretty much straight up or straight down instead of on a slant, that means sunrise or sunset or moonrise or moonset takes about 2 minutes, right? Because the sky has to turn through half a degree, which takes about 2 minutes of time. And so that's how it works out, yeah. Okay, all right. We define 1 parsec, abbreviation PC, equals 206,265 AU, i.e. the distance at which 1 AU subtends 1 arc second. By what we were just saying. The distance at which 1 AU subtends 1 arc second, or equivalently, the distance at which a star's parallax would be 1 arc second. Distance for which P is 1 arc second. And then that gives us a nice simple relation. D is 1 over P in arc seconds, parsecs. So if you know the parallax in arc seconds, the distance to the star is 1 over that in parsecs. If it was 1 parsec away, its parallax would be 1 arc second. If it were 2 parsecs away, its parallax would be half an arc second. If it were 10 parsecs away, its parallax would be 1/10 of an arc second, and so forth. So that's a very simple relation. We usually just drop the P in arc seconds notation, and we just say D equals 1 over P with P in arc seconds and D in parsecs. So it's just a simple reciprocal relation because stars are all far enough away that we can use that small angle approximation. If something's very, very close to us, like, in Earth orbit, you couldn't use this relationship because you'd have to worry about the fact that we've made this approximation that the tangent of P is approximately P when you do it in radians, but for anything realistic, you can just use that relationship. So it couldn't be simpler. If a star's parallax is 0.25 arc seconds, how far away is that star? 1 over 0.25, which is? What's 1 over 0.25?
1 over 1/4.
Which is? 1 over a fourth, which is? What's the reciprocal of 1/4? 4, yeah, right. So just take the reciprocal of the parallax, and that's the star's distance in parsecs. So that's how we determine stellar distances. We measure their parallaxes, and then the reciprocal of that tells you the distance to the star. So how big is a parsec? Okay, well, it's 206,265 AU, but let's put that in kilometers. Okay, we could run the numbers and do that, and so you get this. So 1 parsec is equal to 3.086 times 10 to the 16th power meters, or in other words, 3.086 times 10 to the 13th power kilometers. What's 10 to the 13th power in words? At least in the US, not in Britain, not in the Commonwealth probably. In India, so in India, 10 to the 6th power is a million. What's 10 to the 9th power?
A billion.
Is it a billion? Oh, you do it the American way then.
And that would be a trillion?
Yeah, because the British way is million, thousand million, billion, thousand billion, and so forth. So yeah, to the Brits, 10 to the 9 is 1,000 million. 10 to the 12 is a billion. But here in America, and apparently India, India as well, right? So I guess the Commonwealth said, to hell with you, Britain, we're going to stick to the other way there. Yeah, so this is basically about 31 trillion kilometers is a parsec. That's a lot of kilometers, right? That's very far. In terms of light years, so what's a light year fundamentally? A light year is what distance? It's how far light travels in a year, right? So you just take the speed of light times a year, how far light travels in a year in the vacuum. In terms of light years, it turns out, well, let's see, so 1 light year, if you do the numbers, is 9.461 times 10 to the 12th kilometers. So almost 10 trillion kilometers is 1 light year. Or, so, i.e. about 10, round number, 10 trillion kilometers, or how many miles would that be, roughly speaking? So a kilometer is about what fraction of a mile?
1.6?
Yeah, so a mile is 1.6 kilometers. If you flip it over, a kilometer is about 6/10 of a mile, about 3/5 of a mile. So this is about 6 trillion miles. Right, just good to know. A light year is about 10 trillion kilometers or 6 trillion miles. In terms of light years, it turns out 1 parsec is equal to 3.262 light years. So parsecs are bigger than light years. It's a bigger unit, 3.262 light years. And astronomers now almost exclusively use parsecs for distance rather than light years. You almost always see things in terms of parsecs, except when we're talking to the general public, because the general public tends to find light years more relatable. So our galaxy, the Milky Way, do you know about how many light years across the disk of the Milky Way is?
100,000.
About 100,000 light years across. About how many parsecs is that, roughly? Don't literally did roughly how many?
30 something.
Yeah, about 30,000 parsecs, or 30 kiloparsecs, we say is the size of our galaxy. About 30 kiloparsecs across is how you typically see an astronomer describe it. And then have I mentioned to you folks the scale model, where if you made the astronomical unit like a millimeter, how big is our galaxy? Okay, so in order to impress upon you and anybody else, right? It's because sometimes people kind of be like, solar system, galaxy, whatever, it's all that kind of stuff, they're the same thing. No, they're not. Because if you make a scale model where the distance from the Earth to the Sun we'll make it 2 millimeters, on that scale, the size of the disk of the Milky Way galaxy is the size of the actual diameter of Earth. That's the size of the Milky Way compared to our orbit around the Sun. That's the same as 2 millimeters compared to the actual size of the planet Earth. And so, in other words, solar system and galaxy are very, 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 very different concepts. So go away. But I'm just going to say, not that I don't want to keep you here, but one more thing though. So stars, and we'll say all this again later, but it's just worth pointing out. So if the sun was the size of a tennis ball, the nearest star is another tennis ball that's like in Chicago from here. Stars are very far apart compared to their separations. And so if two galaxies collide with one another, it's a pretty good bet not a single star within them will collide with one another. But galaxies do collide with one another pretty often, because now let's take our scale model and shrink it down a lot. If we make our galaxy, the disk of our galaxy, a foot across, because I'm American, 30 centimeters, a foot across. Anybody know that's 100,000 light years? How far away is the Andromeda Galaxy? I'll use light years. How far is it?
150,000.
That's how wide it is. So if our galaxy is a foot across, Andromeda is a foot and a half across, but how far away is it from us in light years, roughly?
About the same size as the Milky Way.
Much further, much further. About 2.5 million light years away is how far away the Andromeda Galaxy is from us. How many times is that 100,000? 100,000 times what is 2.5 million? Yeah, that's about right? Because 100,000 times 10 is what? So 100,000 times 20 is? So 100,000 times what is 2.5 million? 25, right. So in other words, the Andromeda Galaxy is about 25 times further away from the Milky Way than the size of the Milky Way itself. So the floor tiles in here are about a foot across. So here's the Milky Way. 25 floor tiles away is the Andromeda Galaxy. That's a little bit less than the back room. That's like to the back row. So our galaxy, foot across, Andromeda, 18 inches across, in the back row. That's not nearly as far apart as tennis balls that are like in different cities, right? So galaxies are close enough together to compare to their sizes that they collide with one another on a regular basis, cosmically speaking. And we think the Andromeda Galaxy will collide with ours, right around the time the sun is turning into a red giant, about 5 billion years from now. More to come on that later, but anyway. All right, time for a break. Time for a break. All right, I don't know when 10 minutes elapsed or didn't elapse, but let's get back to this, shall we? Okay, so, nearest star. Sometimes you hear Alpha Centauri, but actually it's Proxima Centauri, which I think it's actually part of the Alpha Centauri system. It's very close to it in any case. So it's probably a triple star system. But Proxima Centauri is a red dwarf star. So even though it's the closest star to Earth other than the Sun, you can't see it with the naked eye. Most of the stars in the universe are red dwarfs, which would be, we can't see a single one with the naked eye because they're so dim. But they're by far the most abundant type of star. Anyway, Proxima Centauri which has P is 0.77 arc seconds, and that says that its distance is 1.3 parsecs, or about 4.3 light years. So even the nearest star is too far away for the parallax to even be 1 arc second. Okay, let's talk about this funny scale that astronomers use to express stellar apparent brightnesses. So part of my job as an astronomer teaching astrophysics majors is to poison your brains into thinking that the magnitude scale is a perfectly reasonable way to express stellar brightnesses, even though brighter stars have smaller magnitudes rather than larger magnitudes. Astronomy is full of these historical accidents where we do things that are frankly kind of silly, such that if we had it to do over again, we would not do it this way. So, the magnitude scale. But we're stuck with it now. And there's just, all the literature, all the papers are done on the scale. So the scale itself isn't too unreasonable. But what's weird about it, again, is that it's upside down, so to speak. Brighter stars have smaller magnitude numbers rather than the other way around. Why is this? It goes back to the ancient Greek astronomer Hipparchus. Ancient Greek astronomer Hipparchus usually spelled like so, around 150 BC, cataloged some 850 stars. About 850 stars. And he assigned them to 6 brightness categories. He assigned them all to one of 6 brightness categories, which we now call magnitudes. And here's what he did. The brightest stars, he said, are 1st magnitude. The dimmest stars he could see with his eye are 6th magnitude. Now, there are stars much dimmer than this, so it's dimmest visible to human eyes back in the good old days when we didn't have light pollution everywhere like we do now. The dimmest stars you can see under a very dark sky are around 6th magnitude. We'd assign them now. So he said the brightest stars are 1st magnitude as a class. The dimmest stars are 6th magnitude. And then when we started quantifying magnitudes, we decided to stick with the idea that brighter stars have smaller magnitudes than dimmer stars do. And if you want to see a logic behind it, it's the following. The person that finishes the fastest in a race, what place did they finish in? 1st, right? How about the next best? 2nd, and then 3rd, and so forth. That's how Hipparchus was thinking, right? Brightest, ooh, that's first class, so to speak. Beyond, below that, you got second class and third class and so forth. So from that standpoint, it makes sense. But what happened is, in the 1800s, astronomers started to be able to quantify the brightnesses of stars, to quantitatively compare them to one another, and they stuck with this idea that the brighter stars should have smaller magnitude numbers. They should not have done that, but they did, and now we're stuck with it, is what it comes down to. So, the advent of photometry in the 19th century photometry, the precise measurement of stellar brightness, the advent of photometry in the 19th century showed that first magnitude stars are about 100 times brighter than 6 magnitude stars. I'm not going to write this all out, but it's quite clever how they did this. So today when we do photometry, we use electronic equipment to count how many photons, for example, we're getting from the star on a CCD digital image. They didn't have that in the 1800s. So what did they do? I think this is very clever. So you observe a star whose brightness you're trying to determine in a relative way to brighter stars. You observe it with your telescope. And then what you do is you point to the brighter star that you want to compare it to, and if you didn't stop down your telescope, if you didn't block part of its aperture, part of its opening to let light through, of course the brighter star would look much brighter through your eyepiece. So what you do is you stop it down. In other words, you cover the front of the telescope with a mask that has a hole cut into it, and that's called stopping it down. And what you would do is figure out how small the hole would have to be in order to make the brighter star through the telescope look the same brightness as the dimmer star did through the whole aperture when you didn't block anything out. And if you found, for example, that you had to make an aperture which was only 1/10 as large as the full aperture of the telescope, if you had to cut a circle out that only had 1/10 the diameter of the full aperture of the lens or mirror of your telescope, well then what fraction of the light are you letting through? If the aperture is 1/10 as big, what fraction of the light are you letting through? It's not 1/10.
10 times?
Nope. So if I have, here's the full aperture of the telescope, and then I have another, I have a stop, where this is 1/10 the size of the full aperture there. Well, the amount of light you're blocking, the amount of light you're capturing is proportional to the area, right, of the lens or the mirror. So 1/10 the diameter, what does that do to the area? 1/100th, right? Because the area of a circle is proportional to, well, it's equal to what? Area of a circle in terms of its radius is pi r squared, or pi d squared over 4, because r is d over 2, right? So it's proportional to the square of the diameter. So if you only have 1/10 the diameter looking at the bright star, and it looks the same as the dimmer star did with the full diameter, that would tell you that the bright star is only 1/100th that the bright star is 100 times brighter than the dimmer star, because you had to block, you only had to let through 1/100th of its light to make it look the same brightness as the dimmer star did. So I think that's clever. They would stop the aperture down until the stars look comparable in brightness, the brighter and the dimmer star, and then you could just say, okay, well, what fraction of the area am I letting through? It's just proportional to the square of the aperture size. And so that's what allowed them to do this, to find out that pointed at a first magnitude star, pointed at a sixth magnitude star, you have to let through only about 1/100th of the light when pointing at the first magnitude star to make it look the same brightness as the sixth magnitude star does to the telescope. Pretty clever. Well, they decided, let's make this official. So it was made an official definition that a difference of 5 magnitudes corresponds to a ratio of 100 in brightness. A difference of 5 magnitudes is a ratio of 100 in brightness. So magnitudes are a scale. As always, every is a syllable. If differences correspond to ratios, why that would be a scale. What am I saying? No, not proportional. Logarithmic is the magic word I'm looking for. All right, logarithmic scale. They're a logarithmic scale. Our eyes don't have an exactly logarithmic sensitivity to brightness, but it's not a bad approximation. Our eyes are approximately logarithmic in their response. Equal ratios of equal factors, if you will, of brightness correspond to equal perceived steps in brightness. Our eyes function approximately logarithmically. So do our ears, as a matter of fact. And there's a great reason for that. The ratio of brightnesses of the brightest things we can see to the dimmest things we can see is on the order of trillions. And so if the brightest things we could see really appeared billions or trillions of times brighter than the dimmest things we could see, your head would explode trying to perceive all that. And also, many things, it would be difficult to deal with the world if you did that, because there's lots of things that are fairly dim and a few things that are super bright, and those super bright things would just completely blow out the dim things if you didn't have a logarithmic perception of brightness. Same with sound. The loudest sounds we can hear, like a trillion times louder or something like that, than the softest sounds we can hear. If it actually sounded a trillion times louder, your mind would be blown. And also, you can just better cover the range of perception. You get better ability to distinguish sounds of different volumes from one another if you have a logarithmic scale, because that compresses the loud sounds and brings up the very soft sounds into kind of a more reasonable range for your perception. And so, using a logarithmic scale for brightness makes a lot of sense, because it also corresponds roughly to how our eyes perceive the world. Do you know what we call the logarithmic scale for sound measurements, for sound volume? You heard of that before? Decibels. Decibels. Sound is usually measured in bells or typically decibels. It's a logarithmic scale where I think it's 20 decibels is a factor of I don't want to say, I think it's a factor of 10 in actual loudness. I'm probably saying that wrong. Have to Google that later. I've forgotten how it works. But anyway, it's also logarithmic. Okay. So if 5 magnitudes is a factor of 100 in brightness, oh, and then the other thing I should mention, and it was decided to keep it upside down. In other words, smaller magnitudes are brighter, because they wanted it to correspond roughly to Hipparchus's categories. Smaller magnitudes are brighter. So if 5 magnitudes, excuse me, if 5 magnitudes is a factor of 100 in brightness, 1 magnitude is a factor of what in brightness? If 5 magnitudes is 100, 1 magnitude is what? Yeah, people tend to say 20, but that can't be right, because if 1 magnitude was a factor of 20 in brightness, what would 2 magnitudes be? In other words, take magnitude 3. If magnitude 2 was 20 times brighter than magnitude 3, how many times brighter would magnitude 1 be than magnitude 2? If 1 magnitude was 20 times, take magnitude 3, magnitude 2 is 20 times brighter than magnitude 3. Magnitude 1 would be how many times brighter than magnitude 2? If 1 magnitude was a factor of 20, magnitude 1 would be how many times brighter than magnitude 2? 20, which would be 20 times more than magnitude 3. So what would be the ratio between 1 and 3 if 1 magnitude was 20 times?
40.
No. So if I were 20 times taller than a bug, and something was 20 times taller than me, how many times taller is that other thing than the bug? If I'm 20 times the bug and something else is 20 times me, how many times is that taller than the bug?
80.
No,
4,000.
not 4,000. 400, right? 20 times 20 is 400, right? 20 times 20 is 400, right? So if 1 magnitude was a factor of 20, 2 magnitudes would be a factor of 20 times 20, 400. And 3 would be 20 times 20 times 20. Whatever that is, 8,000 or whatever it would be, right? And so forth. So that can't be right. So if 1 magnitude, if 5 magnitudes is a factor of 100, you need 5 steps multiplied together to be a factor of 100. 5 steps multiplied together is a factor of 100. So each step itself is what factor? What multiplied by itself 5 times is 100? Correct, but more fundamentally, that is the root of 100. The 5th root of 100, yeah. If 5 magnitudes is a factor of 100, 1 magnitude is a factor of the 5th root of 100, because the 5th root of 100 times 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 the 5th root of 100, 5 steps. By definition, the 5th root of 100 to the 5th power is 100. So keep that in mind. Gets them every time. It's not, right, it's not 100 over 5. It's the 5th root of 100 for 1 magnitude. So since 5 magnitudes is a factor of 100 in brightness, 1 magnitude is a factor of the 5th root of 100 in brightness. Since the fifth root of 100 times 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 the fifth root of 100. Well, by definition, that's 100. So every step's the fifth root of 100. And Estelle, what's the fifth root of 100? Yeah, 2.512 to 3 places after the decimal point. So 1 magnitude's a factor of about 2.5 in brightness. One magnitude is a factor of fifth root of 100 is about 2.512 in brightness. So what about 2 magnitudes, roughly? Well, what would you do? 2 magnitudes, you do 2.512 squared, which is about 6.25 or something like that, and so on and so forth. So, the radiant flux, or just the flux, often we'll say just the flux, from a light source is the energy falling on a unit area held perpendicular to the beam. So we want to hold it perpendicular to the beam because if you look at something at a slant, you don't see its full area. You see only a fraction of the area. So to illuminate something most effectively, you want to hold it perpendicular to the line to the source so that you capture as much light as possible. The energy falling on a unit area held perpendicular to the direction to the source. So as to maximize the illumination. Be sure you understand that. If you don't hold it perpendicular, if it's falling on a slant, you're spreading the light out more. You're not capturing it as effectively. So if I want as much light as possible from the sun, for example, I have to hold my solar cell perpendicular to, the cell itself should be perpendicular to the direction to the sun, held perpendicular to the direction to the source. So it's the energy falling on a unit area held perpendicular to the direction of the source per unit area, per unit time. Per unit area, per unit time. That's what we mean by the radiant flux falling on our detector. So in terms of SI, it's energy per unit area, or energy per unit time per unit area. What are the SI units of energy? Joules. And of time? Seconds. And of area? Square meters, right? So in SI, it's going to be joules per second per square meter. Well, what's a joule per second? What is a joule per second, I ask you? Why, what is that unit? That would be the watt, right? So, in other words, the SI unit is watts per square meter, watts per meter squared for radiant flux. So, this is a measure of how bright something actually appears to our detector. Now, of course, if you have a bigger detector, you're gathering more light from it. That's why telescopes, we want them to be as big as possible. You gather more light for a given flux falling on it. The total energy you're gathering per second, the total watts, is the flux times the area of the aperture of the telescope. We have to distinguish this from luminosity, right? Because, for example, what's the brightest star in the sky? Trick question. What's the brightest star in the sky?
Besides the sun?
The sun, correct. Yes, right? The sun is by far the brightest star in our sky. Does that mean it's giving off more energy than all the other stars in the universe? No. What's the difference between the sun and all those other stars?
The distance.
Yeah, the distance. The other stars are much further away, right? Similarly, okay, what's the brightest star in the night sky?
Sirius.
Sirius. Does that mean Sirius gives off more light than any other star out there? No, it's just relatively close to us, right? And this is, of course, where I have to, maybe you've all heard this one before, joke that was told to me long ago by a student in my Astronomy 111 class. So some of you have heard this before, I know. Star walks into a bar, says to the bartender, "I'm the brightest star in the night sky." Bartender says, "Are you serious?" It's actually a good one, I have to say. Yeah. Okay. So I wish I'd made that one up, but I didn't. Anyway, we have to distinguish the brightness, the flux, from the luminosity, which can be casually described as how bright the star really is, but really it's just, no, the luminosity is the total energy emitted per unit time by the source. So for a star, it's how much energy, it's total energy it's dumping into space per unit time. So energy per unit time, SI units. Energy is, time is, so the energy per unit time is watts again, joules per second, watts, right? So joules per second equals watts, right? So it's energy per unit time. What's the P word that we use to describe that? Luminosity is what's energy per unit time? It's a P word. Power. It's the power, right? Luminosity is the total power emitted by the star in terms of radiation. Watts, that's power, right? It's always important to distinguish between energy and power, right? Because power is energy per unit time. It's a rate. Right, so we have to distinguish between a star's luminosity, what's its actual radiative power, and the power per unit area falling on our detector, which depends not only on the star's luminosity, but also on how far away the star is from us. Okay? If the distance to the star is r, distance to the star is r, and no radiant energy is absorbed along the way, if it's all getting to us, well, all going out and not getting absorbed, no radiant energy is absorbed. Then for an isotropically emitting source, Anybody know what that fancy word isotropic means? Yes.
Same in all directions.
Same in all directions. Yes, same in all directions. Just a fancy way of saying same in all directions. For an isotropically emitting source, the luminosity is spread over a sphere of radius r. By the time you're observing it from a distance r away. Right, so if we are a distance r from any isotropic source, but we're interested in stars here. Here we are. There's the star. Here we are a distance r away. The star's luminosity has been spread over this big sphere of radius r, where r is our distance to the star. So the total power in watts, the luminosity, has been spread over how much area? What's the area of that sphere? Like any self-respecting sphere, as long as you don't account for gravitational bending of warping of space-time or whatever. But anyway, what's the radius? What's the area of that sphere?
2 pi r squared.
No, so close. R squared is right. Pi is right, but it's not 2.
Is it just pi?
No, that's a circle.
4 pi r.
4 pi r squared. 4 pi r squared. It works out to be. No, that ain't.
What am I
No.
thinking about?
I have no idea what you're thinking of. You're just making crap up. It really.
Circumference, okay, I got
Oh, 2 pi r, that's what you're thinking of, probably, right. But it's got to be r squared for the area, right, because it has to have the right units, and r squared has area units, so it's got to be r squared. The 4 part, the fact that it's 4 pi, you just have to memorize it, or every time do the integral. They would give it to you. But in any case, there's a sphere of area A equals 4 pi r squared, right? Spread over a sphere of radius r. So in other words, the flux, watts per square meter, is going to be equal to the total luminosity, watts, divided by that area over which it has been spread, square meters. So the flux is luminosity over 4 pi r squared, as long as it's emitting equally in every direction so that it's spread evenly over the surface of that sphere. Examples of stars that would not be emitting isotropically would be ones with star spots on them, because they look brighter in some directions than others because of the presence of the spots. So then this would be in an average sense that you'd be doing this. The star's average flux would be L over 4 pi r squared. But let's not mess up things like that right now, shall we? So this is what we call the inverse square law for light. Ta-da! The inverse square law for light. So if I get twice as far away from a star, its brightness, the flux I'm receiving, is only what fraction of what it was before. If I double my distance, it's only 1/4, 1 over 2 squared, 1/4 its former brightness. So Earth, 1 AU away. Jupiter, a little more than 5 AU away. Call it 5 AU. What's the sun's brightness at Jupiter compared to at Earth? 1 over, yeah, or that means what? Yeah, 1/25, that's right. You're just giving me giving back what I give, right? Yeah, the answer is, fill in the blank, Dr. Harmon. Okay, I believe you meant 1/25. Was I correct? Excellent. Okay, I'm so proud of myself, yes. So the sun only looks about 4% as bright from Jupiter as it does from Earth. What about Saturn? 10 AU from the sun. Only about 1/100th, only about 1% is bright. That's right. Pluto, 30-ish AU from the sun, looks about, yeah, 1/900th, about 1,000th as bright. Now, lest you think that means that the sky at noon would be, well, that the landscape at noon on Pluto would be very dim and hard to see, I remind you that your eyes have a logarithmic sensitivity to light. And so here's something you might not have guessed. Comparing the sun in the middle of the day to the sun about half an hour after sunset, that's about a factor of 1,000. So noon on Pluto if you look at the surface of Pluto at noon, so to speak, it's about as bright as Earth's surface looks about half an hour after sunset. Probably brighter than you would have guessed, right? And that's because our eyes have a nice logarithmic sensitivity that allows us to have such a broad range of ability to see brightnesses. Yes?
So if you're on Pluto, would it still be dangerous to look at the sun?
It would. We're getting to that. It would still be a little bit dangerous, as a matter of fact, because from Pluto, the sun would subtend about 1 arc minute, because it's about 30 times further away. It subtends 30 arc minutes from here. And that's right about the angular resolution of your eye, your ability to distinguish things. So your eye would be able to focus the sun as a tiny little disk on your retina. And as we're going to see, that disk per unit area on your retina would be just as bright as the sun looks like here from Earth. At Jupiter, the sun would only look about 1/5 as big as it does in the sky, so its image would only cover about 1/25th as much area on your retina. But its total brightness would be 1/25th as large. So if you find the brightness per unit area on your retina, that cancels out, meaning that the sun from Jupiter looks just as blindingly bright as it does from Earth. It just looks smaller than it does from Earth. So you will burn your retina just as surely as you will at Jupiter, at Earth, if you were looking at it from Jupiter. The only difference is you'll simply burn a smaller area of your retina at Jupiter. But burn it you will, and so it is not safe to look at the sun anywhere in the solar system out to Pluto. Now, as you get further away, and your eye and the angular resolution of your eye becomes larger than the angular size of the object you're looking at, then you start to spread that light over the same fixed area. Every star image on your retina is the same size because of diffraction, because your eye isn't able to make images on your retina that correspond to the actual angle or size of the stars. And so this is a good thing, because otherwise, every time you looked at stars, you'd be burning holes in your retina because they would be as searingly bright as the sun. But what happens is, you get far enough away, the image on your eye starts to be set by diffraction. It reaches a certain minimum size, and then as you get further away, the star is putting less and less light over the same amount of area on your retina, and it becomes safe to look at. That's why you don't burn your eyes looking at Sirius from Earth. But if you went close to Sirius, it's got 22 times the sun's luminosity. And so you would fry your eye even quicker at Sirius. And not only that, all that ultraviolet light, because it's hotter. So yeah, don't look at the sun from Pluto either. At least don't stare at it. You can glance at it, right? Shh, don't tell anybody. You can actually look at the sun for a split second, even during an eclipse. The problem is, if you stare at it, the reason why people injure themselves during eclipses is because it looks cool. It looks like a little crescent. Why, that's unusual. And so they forget and they stare at it, and they burn a little crescent in their retina as a result of that. But, you know, we've all looked briefly at the sun in the middle of the day. Did you go blind? No, you did not. But also you didn't stare at it because, ow, right? You know, you just can't do it. During an eclipse, there's just that temptation to keep staring at it. And so, because public health messaging, generally you think, probably should not be nuanced. It should be very straightforward. What we say is, to the general public, never look at the sun, even for a moment, except during totality. During the partial phases, don't look at the sun for even a moment so that people won't be tempted to. But just between you and me, whenever there's a partial eclipse, I go like this and look away quickly just because it doesn't hurt you, just like it doesn't hurt to do that in the middle of the day. It's staring that's the problem. So, shh, let that be our secret amongst we astrophysics types. Don't tell your friends because they might do something silly and stare at it, okay? The inverse square law for light, right there, okay? Now, let's relate fluxes and magnitudes. Fluxes and magnitudes. Of course, the downside of that very straightforward messaging is you get situations where there's been like a teacher won't let their kids go outside during totality because they think that there's these rays that are emitted during total eclipses that make it more dangerous to look at the sun then than it is normally. No, it's perfectly safe to look at the sun while it's totally eclipsed, way safer than it is to look at the sun at any other time. But that's from mishearing the message and thinking eclipse dangerous, eclipse dangerous. Yeah, dangerous when it's partially eclipsed if you stare, if you stare. If you don't stare, you'll be fine. But don't tell anybody. Anyway, fluxes and magnitudes are related via flux 2 divided by flux 1 is equal to 100 to the power of magnitude 1 minus magnitude 2 over 5. Actually, I'm going to do this the other way. I'm going to put a minus on here, even though my notes don't have it. Equals 100 to the power of minus m2 minus m1 over 5. And the minus sign will be there because we want it to be upside down. We want dimmer magnitudes to be larger and brighter magnitudes to be smaller. Which, if you think about it, let's see. So this is 10 squared to the power of minus m2 minus m1 over 5, right? Well, tell me, if I have a to the b to the power of c, what's another way to write that? A to the b to the power of c, it's got a rhythm to it. You take a to the b to the power of c, and what you get is? It's equal to a to the bc, a to the bc, a to the bc. It's equal to a to the power of bc, right? You can do that, right? Because 10 to the third squared is 10 to the 3 times 3 is 10 to the 6, 10 to the 3 times 2, and so forth. So this is 10 to the power of minus 2, m2 minus m1 over 5, right? I've just taken 2 times a fifth in doing that raising to the power there. So it's 10 to the minus 2, m2 minus m1 over 5, minus m1 quantity over 5, which we usually write as 10 to the minus 0.4 times m2 minus m1, but it's understood that there's an infinite number of sig figs there. We just didn't write them all. In other words, that's really the exact number 0.4. That is not a 1 sig fig approximation or anything like that. So F2 over F1 is 10 to the minus 0.4 m2 minus m1. Why is that the relation? Well, what does it need to do? Check. Does this do the job for us? If m2 minus m1 is equal to 5, then F2 over F1, F1 is equal to 10 to the minus 0.4 times 5, right? Actually, that's right, but I'm going to do it in the first way first. So it's equal to 100 to the power of minus 5 over 5, right? If m2 minus m1 is 5, if it's a difference of 5 magnitudes, with m2 being the larger one, then the flux ratio is 100 to the minus 5 over 5. Quick, simplify. What's 5 over 5? 1, right? So this is equal to 100 to the power of minus 1, which is the same thing as 1/100th, right? And so this is saying if m2 is m1 plus 5, it's 5 magnitudes bigger than m1, then f2 is 1/100th of f1. So this does our two things. Is a difference of 5 magnitudes a factor of 100 in brightness? It is, right? Because turn it around, F1 is 100 times bigger than F2, so 5 magnitudes difference is a factor of 100. And it does the other thing where if M2 is bigger than M1, F2 is smaller than F1. So it's also upside down. The minus sign gave us the upside downness of it. So this does what we need. A factor of 5, a difference of 5 magnitudes is a factor of 100, and the smaller magnitude is the brighter one. It gives us what we wanted there. Hold on, folks, unless you want to learn some astrophysics. Okay, so it does what we want. Check. Does that make sense? You mind what I'm selling there? Okay. All right, so delta M equals 5 says flux ratio equals 100. And bigger M means smaller f. That's all contained there. Glorious. One more thing. So, take the base 10 logarithm of both sides. So in other words, if I start with F2 over F1 is equal to 10 to the minus 0.4 M2 minus M1, that says the base 10 logarithm of F2 over F1 is equal to the base 10 logarithm of 10 to the minus 0.4 M2 minus M1. What's the logarithm of 10 to some power? What's the base 10 logarithm of 10 to the x? It's just x, right? Because logarithm base 10 is the inverse of taking 10 to the power, right? The logarithm of number is the power to which 10 must be raised to give that number. So the base 10 logarithm of 10 to the third power is 3. Because 10 to the 3, right, is 10 to the third, is 1,000, right? Right, that's what a logarithm is. So the logarithm of F2 over F1 is minus 0.4 times M2 minus M1. Take the logarithm of both sides. Log 10 of F2 over F1 is minus 0.4 M2 minus M1. So this says M2 minus M1 is equal to minus 2.5, which is the reciprocal of 0.4. Right? 0.4 is 2/5, so its reciprocal is 2.5. Minus 2.5 times the base 10 logarithm of the flux ratio. So that equation gets a box, and this equation gets a box. In other words, this equation says, if I know the two magnitudes, this tells me the flux ratio. This equation says, if I know the flux ratio, this is the difference in magnitudes. They're just inverses of one another. So we'll stop here, but I'll note, all we have done is defined how to find the difference into magnitudes in terms of the flux ratio, what we would still need to do is say, okay, but what specific flux corresponds to some specific magnitude? In other words, what we need is a 0 point. We need a definition of magnitude 0 equals this particular flux. We haven't calibrated it. It's all relative right now. Why, next time we'll talk about calibrating these things. So we're done. I think it pretty much stayed awake. Yeah.
So nice.
It is nice, isn't it? Yeah, be alert and awake and, yeah.